Thank you. Very happy to be here. Thank you for inviting me. The title of my talk is a very fast super recognizer for faces running in my GPU. And it basically is about the work we've done over the past 4 years in the Janus project to get to a point where we basically started in September 2014 with very little. And now we are at a point where the system we've developed compares very well with super recognizers. And it has the fundamental difference that while a super recognizer may be able to do some 6, 10, 12 comparisons per minute, our system can do in that same minute a couple 100,000 face-to-face comparisons. All right, so I have to put this here. I'm just a guy that came here to give a talk. These are not positions of the government. I'm just a guy that is funded by a research contract from IARPA. And yeah, that's it. Right, so other than what I've already said, this talk is also about our evaluation of the system we've developed and what we've learned, what has worked for us, what has not worked for us, and understanding how we can improve the system and where we can go in the task of building computer systems that are able to recognize faces. So just add one more comment here. I'm surprised. I hear all these people talk about how they're using computers to understand how the vision system works and how we process faces. And I'm building computers to recognize faces, but we face exactly the same problems every day. So it's surprising that the vocabulary is a little bit different, but it's exactly we do exactly the same thing. So I'll try to make the comparisons and the analogies clear as we go along. All right, so to understand where we are right now, it's important to maybe explain what has happened in face recognition over the past 12 years. So this is a data set. It's called CMU Pi, came out in 2003, okay? And these were images that back in 2003 were at the edge of the state of the art. Okay, there were systems that were able to, algorithms that were able to handle this, and there were algorithms that were not able to handle this level of complexity. So here you see one person, and the way that these images were acquired was as follows. A person came into a room, there was a dome with different flashes and cameras, and in a couple of seconds, it acquired several hundred images of this person. Okay, and you see that it's very clear that this is the same person. The appearance changes significantly, and the identity is remaining constant. So these were difficult things, difficult tasks in face recognition a short 15 years ago. Okay, so Pi means pose, illumination, and expression. I'm showing you illumination part. There was also a pose part in Pi. And you see that, these images, there's significant misalignment, and there's foreshortening on one side of the face, but still both eyes are visible, and this is what today would be a trivial image to recognize, a trivial face-to-face comparison to make. Back then, 2003, 2004, 2005, even 2006, it was routine in our area to have to do hand clicking to perform the alignment of the faces. Those are problems that in the past 10 years, we've completely overcome. And particularly, it was acceptable to do hand clicking when there was significantly off frontal faces. Right now, we have systems that are able to automatically locate these key points for alignment across the whole pose continuum. So there were images in CMU Pi that back in 2006, 2007, we knew were beyond the state of the art. Back then, when I started my PhD in 2005, this image in which this person and the image on the left was only showing one eye was considered to be beyond the state of the art. At one point in the future, we would be able to handle this, but it wasn't in the immediate research plans. So let me give a quick overview of the types of methods we were developing back then some 10 years ago, 15 years ago, between 10 and 15 years ago, and they all followed exactly the same pattern. Okay, so you would take the image, you would compute gradients. If you wanted, you could optionally smooth the image before computing the gradients, and then you would pool the gradients, okay? And then this would generate some type of description of the face, and you would train a classifier to determine on these descriptions whether these are pairs of the same face or not. So common algorithms back then were histogram of oriented gradients or dense histograms of oriented gradients, in which you would just build the histogram, compute the gradients, and then go ahead and build the histogram. And then the similarity of the faces was the similarity of the two histograms that describe the faces. There was another method that was a little bit more sophisticated, in which you did some non-linear parts. The descriptor was 1, 0, depending on if the central pixel was greater than its neighboring pixel. And then you would build a histogram around the neighbors and compare the histograms. But the ideas were kind of like this, okay? And the different algorithms had different ways of computing the gradient. Some people like to do the smoothing, but they all follow this same pattern. And so it turned out that we were onto something. But what we needed was more power in our algorithm. And I'll be clear on what I'm trying to say in a couple of slides. So in 2008, due to several changes in the world that were completely outside our control, face recognition changed. Now, the images were not acquired in a lab setting when you stepped into a cage that had flashes and cameras, but the images were acquired by cell phones that people had in their pockets. So everybody had a cell phone in their pocket, and the camera quality of the cell phone that people had increased in quality in the first few years of last decade. So, and this all became very clear, and this is hindsight. This all became very clear in 2008 when Labeled Faces in the Wild came out. So Labeled Faces in the Wild are just collections of images from news stories that occurred between 2002 and 2004. Okay? So now the images are not acquired in a cage, carefully, synthetically. Now they're acquired by a professional photographer that's taking pictures of diplomats and politicians and actors. Okay? And still the images were mostly frontal, and they were significantly more difficult than what was being done at that point in face recognition. And it was eye-opening to the face recognition community that we had developed all of these algorithms, and they weren't really working on the images the world cared about. So let me draw a small picture here of the situation in 2008. Okay? So this is the universe of faces. This is the subset of faces that were detectable, and the algorithm that was commonly used 10 years ago for face detection was called the Viola and Jones face detector. And this subset right here is what was the faces that we were able to detect, and then we would be able to process and recognize. Okay? So this was the situation 10 years ago. Still, in Labeled Faces in the Wild, there are still some images that by today's standards are difficult. For example, politicians look the same every day. Diplomats look the same every day. They have to cater to this brand. So for example, if you were building a model of Kofi Annan's appearance, you would say that he rolls out of bed with a three-piece suit and that little tilt in his face and that expression of diplomatic understanding. Of course, Kofi Annan doesn't look like that all the time. Kofi Annan smiles. Kofi Annan smiled. Kofi Annan opened his mouth. Or Kofi Annan blinked. Kofi Annan did many things. But based on this sampling, you would think that this person always looks like this. So there were actresses, and Anna Kurnikova would want you to believe that she rolls out of bed like that. She doesn't, and she changes her look significantly. All of these actresses change their look significantly. There are images in LFW that come from event photography. For example, tennis players that are hitting a ball and things like that. So there are still difficult images by today's standards in LFW, but they were a minority. Okay? The vast majority of them had this bias towards event photography of diplomats and politicians that look the same all the time. Around the same time, there's this work on the good, the bad, and the ugly. And these were images that were acquired at the University of Notre Dame. They were mostly frontal images, and they were taken throughout a couple of academic years. These images were acquired both indoor and outdoor, and it had the thing that the authors behind it were in the area of behavioral analysis and face recognition from the behavioral side. And the images are carefully analyzed, and we had at that point a good understanding of what faces were easy, the good, what faces were okay, the moderate, and what faces were really hard, the ugly, which are the right column over there. So what we learned? What did we learn? What was the breakthrough that allowed us to come and be at this point right now? So gradients, which were the beginning of every algorithm we were using back then, are just a simple type of convolution. Building a histogram is just a pooling operation. And we can learn the convolutions to describe the faces from data. The only thing is that we need lots of data. But then again, a baby monkey needs 8 months to learn faces. That's a lot of images that monkey's eye is capturing. So that's OK. We'll just handle the issue that we need faces. So we had a breakthrough here, which was AlexNet. AlexNet has 5 convolutional layers. This first layer called C1 is what in this community would be called V1. The only difference, I believe, is that when the image gets there, the acquisition process has been completely done. We have an image. And then there's the subsequent layers. And then at the end, we have FC8, which basically is how we connect the training supervision to it. So in this case, we were learning a 1,000 class classification model. But when we're going to use this network, what we do is we decapitate it, or we take the head off, and we use FC7. I call FC7 the descriptor. I believe you, in this community, call it the high-level object code. And I believe in monkeys that would fall in the IT. I may be wrong. So, all right. So let me just emphasize. Back then, 10 years ago, features were fixed, and we learned classifiers on those fixed features. Now, the features are learned from data, and the classifiers are trained on those learned features. There was a talk, the first talk this morning had a beautiful word, I forget what it was, to express this concept that in repeated interactions with the environment, the monkey learns what faces look like. This is exactly the same process, but in a DCNN. All right, so why has this DCNNs are an old idea. So the question is, why did this not work before? And let me just give you a list of the insights that have happened, that did not happen in the mid to late 80s, but happened from 2012 onwards. The first insight is that the deep network is just a way to describe faces. A deep network is just a way to describe objects. So we use the previous layer before the last one as features for recognition. And it turns out that these features are very generic. In fact, in the 2 talks ago, we were using AlexNet as a description for faces, where AlexNet is trained on object categories. So these features are very, very generic. The way we add non-linearities is different. Back then, we used sigmoids and hyperbolic tangents. Today, we have a family of activations, ReLU being one of them. These turn out to be relatively important. I think the most important change that happened that we didn't have in the mid to late 80s and we have today are very fast CPUs, a lot more storage, a lot more data, a lot more images, and GPUs that make your computer go like 30 or 50 times faster than CPUs. Okay? So that, I believe, is why this didn't fall into place in the late 80s, and we had to wait up to 2012 for this to start really working. All right, so after AlexNet and after things started to show significant progress, deep convolutional neural networks started being everywhere. We have a variety of architectures. Here, these are three. VGG is one of them. ResNet is another. We've used all of these types of networks throughout the project, and we notice small differences in using one versus others. But the networks themselves don't generate the difference. What's important is how you connect the loss functions at the end to train these networks to make them good at determining the differences between phases. Right? So data sets to train these deep networks, there are data sets out there that you can go and download, or you can sign fairly trivial paperwork. And you can get data sets with 10 million images, with 3 million images, a couple 100,000 images here and there. And these are all things that are out there ready for you to use. And that's for academic purposes. Now, in companies, well, there's what they say, and there's what they actually do. So they say they train images with 200 million, train networks with 200 million faces. I'm sure they train with a lot more than that. But yeah. All right. So now in this project I work on, the task is first, it's really unconstrained. It's not LFW unconstrained. It's unconstrained for real. So the thing is that we get evaluated a couple of times a year on images that the government cares about. Okay, we don't get to use the images that everybody in the community is looking at. The government goes out and commissions a company to build a data set to evaluate us, the different performance in the Janus project. So the CS data sets, CS2, 3, 4, 5, and CS6, are internal data sets, but as we use them and as they evaluate us with them, they make them available to the public. So they have made available IJBA, BB, and BC. So one of the things I believe that they wanted to do is take this photographic bias out of the middle, and I believe they've done that successfully. The way they did this is that they give you half images and half just randomly selected frames from videos. And we have a large variety of tasks that we need to do. So there's one task which is verification, in which we have to build a template of one identity. A template is just a collection of images of the same person, and we have to process those images and generate one description, and generate a description of another set from another set of images, and generate a comparison. There's search, in which we define a gallery, and then the people, we get a probe, and we need to find the item in the gallery that's closest to the probe. There's covariates, there's clustering, there's uncurated search, and there are even video probes. So let me just make sure I clarify the difficulty here of the different tasks. There's this set here which started with CS2, then they added new images, which is CS3, and they added more images, and it's CS4. And then they made available a new data set that had some of the difficulty in the CS4 and CS3 and CS2, but also came with new difficulty, which was that they defined a gallery of 1 million identities. And then after that, they came out and they said, oh, OK, so there's one other task I care about, which is surveillance-type face recognition. So we have videos and cameras looking at people from above, and that is CS6. So let me give you a small rundown of the highlights. So template-to-template verification tasks in CS5 includes 10 to the 12 evaluation pairs. That is 1 million. That's a trillion. So one-to-end template search in CS5 includes a gallery with 1.1 million templates, or 1.1 million identities. There's uncurated search to search. They give you an image. They don't tell you who's there, but they tell you, don't tell me don't tell me where the faces are or anything. Just tell me the matches in this gallery, and that's completely uncurated. You don't know. You have to build identities yourself. There's clustering, and there's video uncurated search. So let me add one more thing, and I'm gonna give you a very clear example. If you wanted to build an algorithm that's good at one of these tasks, that would be really easy. That would be like Usain Bolt running 100 meters. And we would just tune the algorithm to the task. On his left is Mo Farah. He's the world champion and current Olympic champion at 5,000 and 10,000 meters. So it turns out that when you're running 25 laps instead of half a lap or 1/4 lap like Usain Bolt, being a ball of muscles really isn't to your advantage. So, and over there is Joe Kovacs. He's the American and Olympic champion in shot put. Okay? So you see that the only thing that is well developed in his physique are those arms he has. Okay? So what we don't want is to tune algorithms to tasks. What we really want is the Decathlete. Okay? So the Decathlete doesn't get to compete only in one event. He has to be good at these 10 events. Okay? All right, so I will now go over the things that I believe are successful in our approach, and here we go. So the first one is that we need to be reliably able to detect and obtain key points and estimate the attributes on images like this. That was our first order of business. And our idea was to handle all of these tasks that include identification, key point location, yaw estimation, gender estimation, ethnicity prediction, and all of them all at the same time. So this is building on the observation that if you know where the mouth is, you'll be able to say if this person is smiling. If you know where, in what direction, what the yaw is, and what direction this person is looking, you should be able to locate the eyes. So there are many chicken and the egg problems in estimating these attributes, and we think that it would be better if we all solve them at the same time. So I learned in London a few months ago that Brad has an equivalent approach and has evaluated evidence that that people that are really good at recognizing faces, they're also really good at other face-related tasks. So when we were working on this, I was really not aware of any of these connections. So this all builds on an idea from machine learning, which is called multitask learning. And here, and this has to do with a question that came up in the previous talk. So how do you know where to take features? And so we carefully looked at that, and we had a variety of tasks we wanted to handle. We wanted to estimate smiling. We wanted to estimate roll, yaw, and pitch. We wanted to estimate the key point location, the visibility. We wanted to estimate the age, the gender, and additionally, we wanted to compute an identity descriptor. So basically, Rajiv, who worked on all of this, he tried all possible permutations. He tried grabbing features from all layers of the network, all possible permutations of this, and he converged to what was clearly the best option. And this best option has the characteristic that near the top, he's grabbing features for shallower, easier tasks that are independent of identity. And for other tasks, they are deeper and more difficult tasks. So subject-specific features are pulled from deeper layers of the network. Subject-independent tasks like detection and key points are taken from the levels up there. Again, a fully 100% university-based Janus performer. We took publicly available data sets, and this was around the end of 2016. And this is the amount of data points we were able to collect that were already pre-labeled and we were able to download from the web. And these are the loss functions that we're training. So this compares very well to other systems, and specifically, we're not a system to only determine age, but we compare very well to systems that are solely were developed solely to estimate age, for example. We're also very good at estimating the precisely locating key points and estimating yaw, post-estimation. And here you see that we're able to handle key point location precisely across the post continuum. In addition to being able to estimate the key points, we're able to get age relatively precisely from different individuals, and we're able to match them to a predefined gallery we have. So we're solving all of these problems in an all-in-one fashion.
Can you show the yaw estimation again? Previous slide. There we go. Nope, that one.
Yep.
So what's your average error in degrees?
For about half the images, we're about at 5 degrees.
5 degrees?
Yes. All right, so this Alice talked, so I'm going to go quickly over this one. Alice talked about this, and this is something we published in FG16. This we can obtain from the norm of the descriptor. We can obtain an estimate of quality. Okay, Alice already described this work. Rajiv took these results. He was inspired by them, and he further evaluated them. So, so here we get. This is an ROC curve. This is what I call false accept rate. I believe people in this community like to call it probability of false alarm. And this is what I call true accept rate. I believe people in this community like to call it recall. Observe that this axis here is in log scale. So the observations here is that there's significant amount of difference when we get to compare two high norm descriptors, which generates this red line up here, and we need to compare, for example, two low norm, low quality descriptors, and that generates this blue line right here. So this it's got us thinking that perhaps we need to limit somehow the ability of the network to assign an arbitrary norm to its items. So right now, at this point, what we were doing is, well, the descriptors can fall absolutely anywhere. And what we propose is, well, let's force the descriptors to fall on the surface of a given hypersphere. This is controlling somewhat the capacity of the network and making it not be able to throw stuff here in the garbage dump when it's not sure, forcing it to put things on the edge, on the surface of the hypersphere. This, so this has a very simple implementation in the tools we do. We basically just normalize and assign a radius. This radius, alpha, is the norm of the descriptor we want to generate. So let me give you an analogy of what we're trying to do, and this works significantly better, so I'll try to explain it. So the analogy is, let's say you have marbles on a table. If the table is too small, there won't be enough space, so you'll probably give up. If the table is too big, you'll probably be wasteful, and you won't be neat in organizing your marbles. But if the relationship of space to colors, to number of marbles, is just right, you will be able to organize the marbles on the table in such a way that now, after you've organized them, if I give you a marble of a color you've never seen before, you will be able to tell me where on the table you should put it. So this generated significant differences when compared to softmax, which is what is commonly used. So we evaluated the embedding quality, and we saw significant differences. And we saw tighter clusters when we used the L2 normalization, which we call crystal loss. The distribution of match cores and non-match cores include more things towards the edges when we do this normalization. So this is one of the key insights that has allowed us to obtain the level of results we're getting in recognition. All right, so this is our pipeline. It's very straightforward. We detect faces. We get key points with UltraFace, as I just explained. Then we use a network which we call Rajiv G1. Rajiv G1 is just dealt to softmax. We do triplet loss embedding. This is not fundamentally important, nor am I going to explain it here. And this gives us a descriptor. This is all we do. We've improved a little bit on the ability to recognize faces. So you see this is more or less the level at which we are now. And compared to the plot I showed at the beginning, this is more or less how I believe we are. There are faces. There's a small number of faces that are still undetectable. There are still faces that we're able to detect that we would not be able to recognize. You can see it could be that this is my brother, and I would not be able to recognize him. But that is more or less the situation right now. So results, this is where we are currently on LFW. So consider that in 2005, getting 65 or 70% on LFW was really, really good. Now we're getting 99.8%. And it's not really used anymore for benchmarking purposes other than just a sanity check. So these are results of UltraFace compared to other systems on IJBA. Remember which one IJBA is. IJBA was probably the smallest of the data sets. And this is softmax or L2 softmax or crystal loss. And this is probably the best numbers we have up to now, and currently the best numbers on this data set. So here I want to go over quickly the results. Again, this is a one-to-one template-to-template comparison verification experiment. Again, this is the probability of false alarm, and this is how many intrapersonal, this is what percentage of the intrapersonal pairs we're recalling. So for example, if we were able to accept 10 power minus 6, this is 1 in a million, we would be able to recall about 80% of the intrapersonal pairs. Okay? And here, this experiment wasn't even run by us. This was run by the government. The government compared to other systems available to it and other systems that you can download from the web. So this is CS5. You see now that you can go a lot farther on the left-hand side. And these images in CS5 are not specifically difficult. They're more frontal. So we do a little bit better. 10 power minus 8, we're about at 70% recall. So this is an experiment. This is an experiment in which we define a gallery with the 1.1 million individuals, and we evaluate what a rank 1 is. Basically, rank 1 is that we find in the gallery as the best match the identity of the person that we're currently probing. And we see that at rank 1 with 1 million items in the gallery, we're about 97%. If we are allowed up to rank 30, which is probably what an analyst would be able to check by hand, we are at 98%. So important here is that this is a closed set metric. So rank is only defined if the matching item is in the gallery. So we also get evaluated on these metrics that are open set metrics. This is the FPIR, probability of accepting a person not enrolled in the gallery, and the FNIR, probability of rejecting a person not enrolled in the gallery. So this plot is low and to the left. A perfect system, you would want it to go right here. Okay? And these are 2 generations of our system. For example, if you wanted the probability of accepting a person not enrolled in the gallery to be 1 in 100, the probability of rejecting a person enrolled in the gallery would be about 10%. Consider that this is a huge, huge gallery. Okay, so the last 7 minutes, I want to talk about providing value. Okay, so I went very quickly over the experimental and evaluation results, just because I didn't want to overdo it. So the real question is not what the TPIR or FPIR of this little button here in my cell phone is. The question is, does it provide value to me that when I put my finger, it unlocks it? Okay? So I guess the ultimate question of is this good is compared to what humans of differing capabilities want. Comparing the abilities of the system to humans of different capabilities. So basically, students, apparently students, and I don't work on the behavioral side, so you'll have to excuse me. Students are stand-ins for the population at large. Fingerprint examiners are important because they have forensic training, but they're not specialists and have not been trained on faces. Super recognizers are people of significant face recognition ability, but otherwise no training. Reviewers are professionals that are dedicated to reviewing faces, but they're not trained to speak in front of the jury or go to the courtroom. And examiners are the highest level of training, and they can do absolutely everything. And the data set, because examiners and reviewers take about 8 hours a pair, in those 8 hours I would do trillions of comparisons, but reviewers and examiners take about 8 hours a pair, we were only able to run a test with 20 carefully selected pairs. So the experimental protocol is humans rate the pairs on a 7-level scale. The algorithms get the image. We detect, align, and compute the descriptor. For the 40 images that form this data set, it took us, typing included, maybe 2 minutes. And so we want to know, how do the algorithms compare to humans of different levels of ability on really difficult frontal pairs? And this is where we are. We see that the best system, which is basically a generation of Rajiv, one generation ago of Rajiv G1, I would say Rajiv G1 would be a little bit above that. That's on my to-do list. But that is the previous generation of Rajiv G1. It's significantly above the median for super recognizers. And it's above the median for reviewers. And it's close to the median for examiners. Okay? So this tells us that there's great space here to really provide value for our users. Now, one more thing, and this is really cool. I'm almost done here. So fusing the assessments, for example, the median area under the curve of one examiner is up there. The standard practice is you take 2 independent examiners, and that gives you improvement up there. But if you take 1 examiner and the best system from UMD, you get that result up there. Okay? So this argues, and I'm going to use the words of a journalist that wrote us an article. Please don't Google this article. Please don't read it, but I love the title. Facial recognition experts perform the best with an AI sidekick. Okay? So we've learned so many things in this project. Appearance, first thing is first. Appearance is not identity, and identity is not appearance. They're different things. We have a model that models exactly what we want, which is identity. Important thing, amount of data. We want lots of images of many identities, and data that's clean and carefully curated. We want loss functions that are tuned to the nature of face recognition and converging to useful solutions in data sets with many classes. We're training with 55,000, 60,000 different identities or different classes. Alignment still is very important, and getting accurate key points across the post continuum is important and enables accurate alignment. So those are the things that have really worked for us. Now, on the negative side, things that really have not worked for us Could easily be that we haven't tried hard enough, or we're not lucky, or that's not aligned with with our strengths. It could be anything. We tried different architectures, and so long you're using an architecture published after 2016, pretty much they all work very close to each other. The important thing is the loss function, not so much the architecture. There's this family of approaches that do 3D to frontalize. We haven't had luck, and it basically boils down to the images we fail on are the images that are beyond the state of the art in the capabilities of frontalization. So we gain no value from frontalizing. And in fact, it just adds noise to our system. And motion in video processing, we have not seen much gain yet. We just process everything with the exact same pipeline. We don't do anything special for video processing, and this keeps our pipeline simple. Things we don't know, and I think these are the things we want to look at, is when you have a lot of training data and the training data is fully labeled, the solution is easy. You follow the path we followed. But what happens when you walk back one of these two requirements? Let's say you don't have a lot of training data. Or let's say you do have a lot of training data, but it is not all fully labeled. What do you do in those cases? That's an important question we want to look at. And then there's the real question of the AI sidekick. Please don't use that selection of words. The real scientific question is, how can computers and humans work together in verification and search tasks? And one final slide, and this is something that Rob asked me this morning. So 2006, this was about the limit of the state of the art. 2012, this was about the limit of the state of the art. 2018, this was about the limit of the state of the art, and we're up there with the highest performing humans. I would not want to give you a prediction for where we would be in 2024. But you have a tendency of what's going on in this area. Thank you very much.
I have two questions.
Yes.
One is more a science question, and one is more an ethics question.
Yes.
So.
Can you start with the ethics question?
Okay. So I live in Silicon Valley. I have friends in Google, and one of my friends told me that, and you had like some data from Baidu that does actually pretty good in the face recognition task.
Yes.
And user capacity of networks now millions and maybe billions of faces.
Yes.
So I forget what Chinese city is. I'm not very good with names of Chinese cities, but they had the problem of people not obeying traffic laws. So what they did is that they put cameras on this busy intersection, and every time somebody maybe crossed the street in a red light or something like this, the algorithm can recognize them right away and then say citizen, whatever their name is, and the full name and stuff, disobeyed the law. So first of all, this is kind of like public shaming, which is unpleasant. But given that this is China, if you have too many red points on this billboard, you might have a real problem finding a job or stuff like that. So the question is really like, you're doing a project that's funded by the government. I know terrorism is a big deal. These things could help us find criminals, but this also has this kind of like Big Brother vibe. And maybe you could say something about it. Should we be worried about it? Is there somebody thinking about having laws, what's okay to do and what's not okay to do once we have the capacity to recognize 7 billion faces?
Yeah, so.
That's my ethics question.
Okay, so I'll give you a comment, not an answer. I think that we're doing this. There are also many other things. Like there are consequential decisions that are being made based on an assessment of an examiner, on an assessment of a person that declares, yeah, these two are the same person. That's a consequential decision, and I think that that should be audited. And I think that there's the potential for these systems to make decisions that are as good or better, and scientifically it's our responsibility to get there. There's the policy question, and I'm not a policy person, as to what happens. And I think it's a conversation we need to have. What happens when we get there, or what happens as we get there. And it's important, right? It's how can we use it? We need to regulate this. And you raise a valid about it can be abused by governments, and it's a real problem.
I might just add to that, because I mean I agree with you. But there are other uses. One of the uses that this will be probably these algorithms will be first put to with FBI stuff is there are people now who have to go through child pornography videos to try and keep track of which children are in which locations to locate them, which is a horrible job, obviously. And so being able to use these algorithms to screen through those is one of the applications. So for every good application, there's a ton of bad applications. So, you know, it is really, the policy people are way behind the science. There's no question.
I think the reason I'm raising this is not because I think there aren't really good plenty application. I think this is awesome, and I think it's also inevitable that it's going to happen. And I think because you guys are actually working the government, maybe it would be nice if somebody thinks about these ethics before the algorithms can do it, because it's usually the other way around, that the algorithms can do it, and then, okay, like,
what do we
have
do
any
with it
rules
now?
for that?
Yeah.
Yes.
I think you just captured something really important in that comment, though, which is, given that these systems are going to be used anyway, do we prefer ones that are accurate or ones that are inaccurate?
No, I mean, there's no question that we prefer the ones that are accurate.
It's hard to get Congress to do anything now. Anything they don't have to do like this is just gone by the wayside. Regulating social media and all kinds of privacy is a big issue.
You had another question?
Yeah. The science question is, so both in your analysis talk, you guys had this analysis that said that the architecture did not work so well, but the cost function is really important. And this kind of remind me of Dan Yaman's original studies, that he showed that the algorithm that best matched the IT neurons was the one that actually solved an categorization problem. So that's kind of like saying in human speech cost function. But I was wondering what is the role that plays in the success of the algorithm, the training set?
Oh, the training set is absolutely key. And
so could you tell us, like, what are good training sets versus bad training sets? Do you have any insights on that?
Yeah, so we've looked at it a lot. So you want a lot of images, but it's not just a lot of images. If for a constant number of images, if you could have a low number of identities or a high number of identities, you need to prefer a high number of identities, as many identities as possible. You want highly curated. You don't want gross mistakes, because you're going to be adjusting the network weights based on your predictions on these images. But you want hard, difficult images. And the world, like when you download images or when you acquire these data sets, the distribution of yours is very highly Laplacian. Like a vast majority of images are frontal, and then a very, very quick fall off on the non-frontal part of the histogram. What you would want is very heavy tails and be able to see the variety of poses, and it's really hard. And like if you had to, I mean, and it's very difficult in a university environment, because part of the responsibilities in a university environment is to find nice, beefy projects for students that would lead that are fundamental research. And this is at the point right now. This is basically engineering. This is not fundamental stuff. So it's hard to do this in a university environment, and it's quite challenging. But yeah, we've looked at what makes good data sets good and bad data sets bad. Yes.
So impressive results. So one of my questions is that representation is very important, right?
Yes.
So as Doris showed in her first slide, humans represent objects in contours. And we recognize the cave lines from that image, even though we've never seen a cave line that is just a side view of a small line. But there was some research recently about how if we give the same object in a sketch with just lines, CNNs fail to recognize that as an object.
I would believe that there's no good reason to get a good descriptor if you give me something whose modality is different. Like it could be, there's work on like matching these pictures to sketches, but as is, this is just for computing descriptors of RGB images. So
in your network, for example, the one that works best, if I give a sketch of a person, would it?
It won't work well.
It won't. So if that is the case, then is it an ideal situation to compare these networks with the human representations if they fundamentally differ in how they represent a facial?
Well, so it's in comparing it to humans, I'm not doing something fundamentally outrageous. I'm just trying to duplicate what the FBI case examiner casework looks like. So yeah, he gets a pair of images and he has to say, are these the same person or not? That's the extent of the question. And usually there are standards over the quality of the face and the modality of the faces for these examiners' strength to hold up either as to generate a lead or to be able to present their findings in a court of law. I'm trying to duplicate that in a computer-based algorithm. So yes, scientifically, we could study these types of models in a similar way to the methods that we study the brain, but I'm not saying that this is duplicating what the brain does. I'm not saying that or not anything near that.
But so what?
Yes.
What would be an augmentation for the network to make that work? Like, what do you think is the next step?
Oh, so if you told me that you want to match pictures to sketches, hire me a sketch artist and I'll give him 50,000 faces and he'll generate 50,000 sketches. Or we would find a way to put the descriptors of the faces and the descriptors of the sketches into a common comparable space and then compare the distance of the descriptor to the descriptor of the image to the descriptor of the sketch. It's absolutely doable. And it doesn't, probably the first approach I would take would not entail 50,000 sketches.
Yes. I have to add to this that has already been done. There are algorithms that recognize faces from sketches, and there are databases that are specifically used for that.
Yes.
So your examiners
Yes.
that spend hours
Yes.
matching two photographs? Or did I miss it?
No,
what
hours.
can you do for hours
I
to
don't-
match two photographs?
I don't know.
Really?
They measure, these are the guys who go into court and testify absolute identity. So that top echelon are people who do this for a living, and they were from 5 continents or something.
Yeah.
So, people who do this for a living go into court, say this is an identity match between these two people. So they'll measure stuff, they'll try and estimate illumination, they'll try and figure out size based on where the camera was. It's actually a relatively entailed process, but it produces good results. I mean, I think I was surprised how good they are at this, because they haven't really been tested much.
Yeah.
Certainly not compared against other people, so.
Yeah, but I think it's important to point out that it doesn't make them super recognizers. They're not good at face memory. I
Right,
mean, they
they're
just
not.
do image comparison, and they're not good at face recognition in general. So it's not even face perception, the way
I
we
would
think
say
about it.
Because they're so much better than the fingerprint examiners, what we figured out with the fingerprint examiners who are forensically trained is they use the scale the same way as the face-trained people, very differently than the super recognizers and the students. So the super recognizers and the students use the scale very carelessly. I mean, they'll just, yeah, sure, it's the same person. Whereas the forensic training, I think, actually changes how people use the scale, not necessarily whether they're talented at the task to begin with. So probably the examiners have talent and training to use the scale properly.